Second recording, it shuts off like halfway through. Okay, so as b gets closer and closer to infinity, this just gets closer and closer to infinity. So we know if the integral diverges, the series diverges. As long as it meets those three criteria. Series.
I was like, wait, what? Oh, wait, you keep saying series, so I'll keep going off.
Yep, so as long as the integral diverges, then the series diverges. No, that's it. You know what I mean. So I'm gonna have third class today. I'm entitled to.
Conversion, diverge.
Okay, you're bound to get mistakes right about now.
Right.
But hopefully you know what I mean.
6 hours of calculus.
Keep this
Yeah.
up, you'll be teaching us proof by intimidation.
Yep, so this is your proof there. So we're just going to put that as one clear-cut theorem. Anyone still writing this one? All right. So the convergence of a p-series. Okay, so we know that the p-series sum from n equals 1 to infinity of 1 over x to the power of p, which we know is 1 over 1 to the p plus 1 over 2 to the p, and so forth and so on. We know it converges for p is greater than 1 and diverges for p is less than or equal to 1. Okay, so let's say, for example, if we have, let's say we wanted to determine convergence or divergence of the p-series. Let's say for A, we'll make it the sum from n equals 1 to infinity of 1 over the fifth root of the n. And let's say for problem B, we have 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, and so forth and so on and so on. Okay. Now for A, really all you'd have to do is rewrite your denominator. Okay, so you have the sum from n equals 1 to infinity of 1 over n to the 1/5 power. Okay, so we know here that our p is equal to 1/5, which is less than or equal to 1. Okay, so we know just from the p-series that it diverges. Well, diverges using p-series. Okay, now for B, we know we have 1 plus 1/4 plus 1/9 plus 1/16 plus 1/25, and so forth and so on and so on. Okay, so we can rewrite this instead of 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared etc., and so on. Okay, which gives us the sum from n equals 1 to infinity of 1 over n squared. Okay. So here, our p is equal to 2, which just so happens is greater than 1. Okay, so we know that it's convergent. All right. Any questions on this so far? Yes.
Would it be any constant in the numerator?
Nope, it'll have to be 1. You can always factor out the 1, so I guess it could be any constant,
Right.
technically. All right. Oh, anyone still writing? All right, so let's say, for example, let's say if you want to determine convergence or divergence for the P series, say for problem A here, the sum from n equals 1 to infinity, 1 over n to the 7/8. And for B, sum from n equals 1 to infinity of n to the power of 5e over n to the power of 7 pi. Okay, so we know that the sum from n equals 1 to infinity of 1 over n to the 7/8, our p is equal to 7/8, which is less than or equal to 1, so you know it diverges. Okay. Now for B, you do have to kind of manipulate it a little bit. Uh-oh, let me put my A right here. So if you have the sum from n equals 1 to infinity of n to the 5e power divided by n to the 7 pi, you can actually bring this numerator down and just make it negative. Okay, so you can just make that the sum from n equals 1 to infinity of 1 over n to the 7 pi minus 5e. Okay. And here, if you plug in 7 pi minus 5e into your calculator, you end up round about 8.4, which is greater than 1. So it converges. Uh-oh, series converges. By the P-series test. All right, so any questions on that one? Yes.
So how did you pull the 5e down?
Oh, for that one, you have n to the 5e over n to the 7 pi. Remember, if you have x to the m over x to the n that's equal x to the, you can actually make that 1 over x to the n times x to the negative m,
Right. Yeah.
which just makes that 1 over x to the n minus m. This is what I did there, just brought that down and make that negative. All right. No problem.
If you're better with like dividing by them, you could always divide both top and bottom by n to the 5e.
Mhm.
You get the same kind of a thing.
Yeah.
Just dividing exponents that have the same base just subtracts them.
Yeah, same thing. Right. So the only difference is, let's say if your first instinct would have been to bring that negative 7 pi up, then you wouldn't have been able to use the p-series test.
Right.
So that's the only thing about that. So you had to bring that 5e down. All right. Any questions on that one? All right. Good. I'll leave that up for a few more seconds. All right. Okay, so now we're going to look at the direct comparison test. Okay, so let's say if we just want to notice, just based on the previous test we've used so far, that the sum from n equals 0 to infinity of 1 over 2 to the power of n is a geometric series. Okay, but let's say if you have a little bit of a different look to it of n over 2 to the power of n. That's not a geometric series. Okay, just a little bit different. Okay, let's say if we have the sum from n equals 1 to infinity of 1 over n to the third power, that's a p-series. But the sum from n equals 1 to infinity, let's say of n over n to the third plus 1, is not. Yes?
You need that plus 1 in the denominator for that to be true.
Otherwise, you just simplify it and just do 1 of it instead.
Oh, that's right. Duh. Actually, I want to make it to where it wouldn't be, so I would make it... That's what I get for trying to make up problems in my head. I always forget about those little details. So let's say, better yet, make it n factorial. That'll work. Actually, I looked and I didn't see any n factorial problems in your homework.
I've never seen that before.
Really?
Which so maybe we
There
could
was
just.
one in the second one.
Oh, it
that's
was?
today.
Oh, I didn't
Yeah,
see
we're
any.
supposed to today.
Oh, I didn't see any.
Yeah, they're all throughout.
I was looking for them too. Thought y'all got off easy. Okay. All right, so let's say if we have a sub n equals n to the n squared plus 3 squared, you could integrate that one pretty easily. But let's say if you have b sub n equals, let's say I'll say n squared over n squared plus 3 squared. Takes a little more work. I mean, it can be integrated, but a little more work. Yep, clean up that K a little bit. Okay. So with the direct comparison test, you can actually use, I guess you could say, limits that you already know to find out whether or not it converges or diverges just by comparing them. So I'll show you what I mean graphically before I actually point it out. Okay. Let's say if we let some function, some series a sub n be less than b sub n for every value of n. Okay, so we'll start off with two of our graphs. Now let's say this is our a sub n. And let's say these series of points, that's our b sub n. Okay. So let's say we know that our a sub n diverges all the way up to infinity. Now, if a sub n is less than b sub n for every n value, then that means that if this is diverging upwards, then this one's going to diverge upwards. Okay, so let's say if we have our b sub n, and that's converging, well, we'll say towards 0 or any value. Oh, straighten that up. Then if your a sub n is down here, and it's less than b sub n for every value of n, then if that's converging, this one's going to converge. Okay, so the actual theorem, well, not definition, I guess you can call it definition, the direct comparison test. Is you're going to let an be less than bn for every n. If the sum as n approaches n equals 1 to infinity, I don't know why I did that. From n equals 1 to infinity, if b sub n converges, then the sum,
Move it up a little.
oh, sure. Then the sum from n equals 1 to infinity of a sub n converges, which was this one here. But if we know that the series from n equals 1 to infinity of a sub n diverges, and the sum from n equals 1 to infinity of the series b sub n diverges.